Good afternoon, everybody. Welcome to the Carbon Solutions webinar series. In this series, we highlight work that we're doing at the company and with our partners. My name is Jonathan Oglandhand, and I'm really happy to have each and every one of you joining us today. Today, Kat Sale and Jeff Bennett will be presenting Concord, which is one of our tools at Carbon Solutions, and their presentation will demonstrate how this software can be utilized to identify opportunities for carbon capture at industrial facilities and at power plants. So this presentation is an overview of a technical report that we are releasing this afternoon. And so we're going to provide a link to that and these slides for all the attendees after the meeting. So please note that this meeting is being recorded, and you can view this presentation along with our previously recorded webinars on our YouTube channel. We would like this to be more than a one-way conversation, so we really encourage everyone to share your thoughts, questions, and experiences in the chat. We will have a dedicated time for Q&A after Jeff and Kat finish speaking. So feel free to drop your comments in the Q&A chat throughout the session, and then I will moderate that at the end. So thank you again for being here, and I'll pass the microphone now to Jeff and Kat.
Thank you, Jonathan. Thank you all for being here today. So we're going to share some work that we did primarily over the last year. And so before I get too much farther, got to give a quick acknowledgement. So a lot of this work was funded under a National Science Foundation Small Business Innovation Research, or SBIR, grant. And that was a phase 1 funding. And just always have to do this disclaimer that the work and views are our own and not those of NSF. Okay, so let's get started. So like Jonathan said, we're going to be talking a lot about some work that we'll be releasing later today in a white paper. And we'll primarily talk about the results that come out of that, or Kat will, the second half of this presentation. For the first half, I'm going to give a bit of an introduction into what Concord is, talk about the range of expertise of people needed to make it happen, some use cases for it, and then demonstrate the web application that we have to access the data. Okay, so for doing Concord, we have found that you need a lot of different people from a lot of different backgrounds. So Kat and I are both engineers, but we worked with a whole team of people that you can see here in order to make this tool happen. You need experts ranging from economists to people with backgrounds in GIS, understanding where the infrastructure might get demonstrated, so you understand community benefits and where it could go, as well as software engineering and policy implications. So we have a lot of people who helped us get here, and Kat and I have the privilege of speaking on their behalf and showing off the work today. So what is Concord? So you may be familiar with some of the other software that's being developed at Carbon Solutions. We have a suite of software to help with carbon capture, transport, and storage planning. Concord is the capture part where we are able to assess carbon capture opportunities. The original purpose for it was to help support some of the other software that we had, so to provide estimates of the cost and amount of CO2 that could be captured into the other software, but we have quickly found that there's lots of other applications for it. On the right here, you see a map showing some of the common outputs you might see from Concord, where you have all the different emitters of CO2. Here we classify them by the type of facility, and then we'll show different features for these, such as cost of capture, amount of CO2 that can be captured, or other things. Something else that we found with Concord is that it can be a great starting point or be able to support a lot of different analyses. So, if your goal is to have a facility that has net zero carbon emissions, it's really important that you consider not just the carbon emissions at the facility, but upstream of that as well. So that's when lifecycle assessment comes into play. So Concord is able to help you with that. We have the ability to support waste heat. So a lot of CO2 comes from combustion, and these emissions have other properties to them. One is just tends to be hot, and that heat could be captured and used for other purposes. We've also been able to use Concord to help with estimating health co-benefits. When you do carbon capture, there's other pollutants that get released as well. And for some of the more common types of carbon capture, those other pollutants can be reduced, which leads to other benefits as well. So Concord had this one original purpose, but has lots of different applications. that we found. And the examples that I gave here are things that we have either started working with or have done for other projects. So a little bit about how NCORD works. So NCORD, the first step is taking lots of different data. So we have found that, there are a couple of databases out there with a lot of information, but they're all different. They have the emissions categorized one way or another, or they might have some features in one that are not present in one. And also, there are some emissions that are just not captured in some of these databases, so we need to look outside to find other ways of including that. So you can see a list here of some of the common databases that we start with. So the first step is to take data from all these different sources, put it into a common format, and that way we can use it throughout the rest of the workflow. Once we get all this emission data and associated data such as fuel type being used or type of industry or process, then we start evaluating capture opportunities. So here we identify within a facility the types of different capture, and we call these the streams that are available for doing capture. And so with this, this is a screening level look. So we don't know the exact layout of the plant. We're just using the information to make general observations of, for this type of facility, these types of emissions often get grouped together. So we'll group different types of emissions together. And then once we have these into streams, now we have information on the amount of CO2, some properties of that CO2, and then we can do some estimating of the cost. So that's the next step. So we have two main ways of estimating cost: a literature-based approach, where we use information that's been released in literature or published in studies. And when I show you the demo in a little bit, that's what the results are for there. The second approach we have is to use cost models. So for this, we have advanced techno-economic models, and that is what is used in the white paper and what Kat will be talking about later. The next step of the process is we have all this information, we do some categorization of it to make it easier to digest and use. And the final step is when the user comes in and says, for my particular interests, I want this, and this type of emissions to look at. So getting a little bit more into that filtering step, where you might consider things such as the 45Q tax credit, looking at emissions in a certain area or a certain type of facility, we've come up with 5 primary use cases for using NCORD. So the first one, and a number of these we have already worked on projects for, and could be happy to share more information if you wanted to. So the first example is, what if an organization is planning to develop a CO2 storage site? So maybe they're putting in a Class 6 well application, and they want to find out what emitters are in the area. So you can put it in the coordinates into NCORD and identify all the different emitters nearby and the estimated cost of capture. And that can provide a kind of a calling list of, as you're developing out the site, what emitters might you want to be talking to or start talking to. It can also be used in a different approach where perhaps there's a facility that is emitting CO2 and they're interested in finding out what other emitters are nearby them. Perhaps they want an estimate of those costs to help them figure out, is there an opportunity for a carbon storage hub, carbon capture hub? I won't go through every example, but the last use case I'll point out is to support things like regional and national planning studies, which is what Kat will be showing later for the white paper. All right, so next I'm going to change gears and move to demonstrate the web application. So I'm going to stop presenting for just a second, and now I'm going to share my browser. And so now you can see the web application. And so when you first load it, this is what it looks like. On the left, we have several different ways of looking at the data. So first we have this map. You can hover over and see all the different sources of CO2, get some information about them, facility name, amount of CO2 that can be captured, the sector, and the cost. You can zoom in and look around. You can also go to these other tabs. And here you see this is a supply curve under the histogram tab. And so this gives you a prioritized list of the different opportunities for capture sorted by cost. So if, for example, you wanted to do a study that found that the cheapest way to meet 1,000 million tons per year of CO2 this would tell you everything to the left of my cursor would be the opportunities to look at. Of course, when you're looking at the map for all the cases in the United States, there's a whole spatial component you have to look at. And so that is why this histogram gets updated as you do with different filtering. You can go to the scatter plot tab where you show the amount of CO2 versus the different capture opportunities. So for the literature-based approach, which is what is being shown right here, each industry has a fixed cost, but in the cost model approach, which is what Kat will be showing later, the cost varies as the amount of CO2 capture varies, as well as other factors as well, but that is one of the main considerations. You can also go to the facility data or the industry tab and get more tabular information about all the different facilities being shown. So this is just kind of a way of seeing the information, but then let's do a quick example of what if you want to use this for analysis. So let's just say, first starting point, we wanted to look at emitters in Texas. So we can go to select states, go down, find Texas here, and we see now we just have the facilities that are in Texas. We can switch, and they're all color coded by industry. Now, if we switch back to the histogram tab, you see it's been updated. So the amount of CO2 is quite different, and the volumes for each of these different industries now reflects what is available in Texas. And maybe we come back to this and think, you know, Texas is quite large. Let's change this area of interest. So instead of just saying all of Texas, let's go into a particular latitude and longitude. So I'll put in coordinates that are approximately Houston, and we'll say, what is every emitter within 100 miles of Houston? So now we have this updated list, updated map with the different emitters. And then we can overlay this with some other information. So we can say, well, what are some pipelines either existing or planned in the area? And now we update it and see the proximity of some of these sources or emitters of CO2 and this infrastructure. So there's lots of different ways that you can use it. At the end of the presentation, we'll be sharing a link to this web application for you to explore as well. So I'm going to get the presentation back loaded, and then I'll be handing it over to Kat to talk about the white paper that we are releasing later today.
Hello, everybody. Let me get this back over. All right, so today I'm going to be talking about the white paper that we're going to be releasing. The white paper provides an in-depth example of using Concord to analyze capture opportunities across the contiguous United States. It's a screening level study, so the purpose is to just screen carbon capture opportunities in the United States and is intended to identify opportunities and project costs using publicly available data. It should be noted that this is not intended to replace a front-end engineering design or FEED study that would result in a more comprehensive facility-specific cost estimate based on detailed operations data. Instead, this is a screening level study. It's going to be looking at the contiguous US, and we'll be using our cost models to look at it. And so for this portion, I'm going to be doing 3 separate analyses. I'll first talk about an overview of the entire US, and then we'll look at specific regional portions of the US, and then we'll look at sources that qualify for the 45Q tax credit. Okay, so to start, we can look at the capturable emissions across the US. And so here we can see that the US has a ton of different emission sources. Specifically, they have a lot of capturable emissions from power production. In fact, coal power plants have the highest quantity of capturable emissions across the US at 835 million tons of CO2. Natural gas plants follow it at 624 million tons of CO2. Despite coal power production generating significantly more CO2 than natural gas production, in 2023, only 16% of the total US power production was actually generated from coal, while 43% was generated from natural gas. Coal combustion has an emission factor that's 1.8 times higher than natural gas, meaning it produces almost double the amount of CO2 to produce the same amount of power. And so then in terms of industrial sources, the highest emitters that have the highest quantity of capturable CO2 across the US is from petroleum refineries and pulp and paper production. So petroleum refineries produce 160 million tons of CO2. And most of these emissions are from the fluid catalytic cracking unit called the FCC, wherein the heavy hydrocarbon portion of petroleum is cracked to allow for the formation of common fuels like gasoline and diesel. Indeed, the FCC accounts for 25 to 35% of emissions at a refinery and is the primary source of capturable emissions that we identified with Concord. Pulp and paper production produces 140 million tons of CO2, and 75% of these emissions are biogenic in source, which means that these emissions are from biological processes or even from the combustion of biogenic or biomass material like pulp and paper. If these emissions are captured, it can contribute to generating net negative CO2 emissions. And so once we've evaluated the capturable quantities of CO2 across the US, the next thing we can do is apply the cost models. And so here we've applied the cost models to all sources across the US. The values here are in 2022 USD, and they have a $500 per ton cap put on them. In red, we have the highest cost, and blue is your lowest cost. And then the sides of our circles indicate the quantity of capturable emissions at each location. In general, there's a trend where high emissions have a lower cost. So if you have more CO2 going through a single piece of capture equipment, that cost per ton of CO2 is going to be a lot lower. But there are some exceptions, such as high purity or high concentration CO2 sources, like from ethanol production, oil and gas production, or natural gas processing. Essentially, if you have a high concentration of CO2 in a stream, then you have the requirement for less equipment. And essentially, you can just compress that stream in order to get it to pipeline quality, which allows for a lower initial capital investment. So one final thing to point is that sources are likely to reach your $500 per ton cap if they're too small for the cost model to generate an appropriate estimate, in which case an alternative equipment configuration, sizing, or equipment type would be necessary to explore. So next I want to pull up these sector supply curves. So supply curves sort the capture cost from each facility, lowest to highest, to identify the least cost option for meeting a capture target. Jeff showed us some supply curves using the literature-based models in the app, but these are from using the cost models. And in general, we can see here that the cost of capture for most US emissions is below $170 per ton for both power and industrial facilities. And so in brown here, we have all of our sectors, blue is our power sector, and orange is all other non-power industrial sectors. So below $170 a ton, that accounts for about 2,100 million tons of CO2, or 85% of the total capturable emissions identified in the US, with about 2/3 of those emissions from power generation, and the remaining like 700 million tons from industrial emissions. And then above $170 a ton, the capture cost begins to increase exponentially, which is partially could potentially be explained as, part of the cost models, but is an interesting thing to explore further. So next, let's look at some specific industrial sectors within the US and what their supply curves look like. So the primary variation between these different industry curves is determined by the amount of CO2 per stream, so the amount of CO2 that's actually captured by a single capture system, and the average capacity factor estimated for a plant, which determines the size of capture system required. So essentially, if you have a plant that operates at like 75% capacity, you would still want to size your equipment to be able to handle 100% of the possible CO2 generated by that plant. And other variations are from the baseline cost for equipment. And on average, that cost is going to increase if you have a lower concentration of CO2 in a stream, i.e. that requires a higher energy investment in order to be able to get a more pure stream of CO2. So some things to point out here is that we have refineries here in green. These are our highest quantity of capturable CO2, and 90% of these streams exhibit are below $150 per ton, and 45% of them are below $100 per ton. The next one to look at would be like pulp and paper here, this brown one, where 89% is below 150 and about 22% is below 100. And then there's two big hard to decarbonize sectors like iron and steel and cement, where in iron and steel, we identified that 67% of those capturable emissions are below $100, and for cement, 47% is below $100. Another one to point out here is ethanol, this orange one right here, where you can see it's some of the lowest cost of capture overall. And that's again because of its relative high concentration of CO2 in the stream. So now that we've kind of looked at the entire US, let's look at a regional analysis. So these are capturable emissions across the US for the different US Census regions. Of these regions, the South represents 47% of total capturable US emissions, followed by the Midwest at 29%. And regionally, coal dominates the capturable emissions in 2 of 4 of our regions, representing the greatest portion in both the Midwest and the West here at 48% and 39% respectively. However, natural gas power production emissions represent the largest percentage of capturable emissions here in the Northeast at 51%. And emissions are split evenly actually between coal and natural gas in the South at 27% and 28% respectively. And within the non-power sectors, ethanol production produces the largest portion of capturable emissions in the Midwest at 13%, which may be expected. And refineries are the predominant sector in the West at 10%, pulp and paper in the South at 9%, and solid waste combustion in the Northeast at 6%. So next, let's look at some supply curves for the different regions. Here we show the breakdown of CO2 capturable in exclusively the industrial sector for below $200 a ton for each region. If we were to look at the power sector, you kind of just see coal. So it's important to look at these other industrial sectors as well. So depending on the region, the largest sector of low-cost CO2 varies, and pulp and paper is the largest source of low-cost capturable emissions in the South at 30% of the South's industrial emissions, and 80% of these are pulp and paper emissions, which are, or 80% of these pulp and paper emissions are biogenic. In the Midwest, ethanol is a large majority at 43%, and in fact, 83% of all ethanol facilities in the US are located in the Midwest. In the West, refineries represent the largest portion of below $200 per ton CO2 at 34%, and in total, they account for 34 million tons of CO2. And in the Northeast, solid waste combustion accounts for a majority of the low-cost industrial capturable emissions at 31%. And industrial emissions from the Northeast only account for 8% of all industrial sources below $200 per ton, meaning that the capturable tonnage from the Northeast solid waste combustion is actually comparatively small at only 12 million tons total. So as you can see here, the South clearly has most capturable emissions, the Northeast much smaller. So if we move forward, let's look at a 45Q analysis. So a primary use for Concord is screening for low-cost facilities. Per the 2022 amendment of the U.S. Inflation Reduction Act, the U.S. 45Q tax credit offers $85 per ton of captured and geologically sequestered CO2. This map shows all capturable sources across the U.S. that are estimated to be capturable below $85 per ton, and the cost of transport and storage is not considered here. There are 94 coal power plants shown, and together they represent 74% of this low-cost capturable CO2. Ethanol plants also retain a low cost of capture despite producing comparatively small amounts of CO2 per facility. At only 7% of the total 45Q capturable emissions, 77 ethanol facilities have CO2, which can be captured for less than $85 per ton. And essentially 2 types of plants are left when investigating these low-cost options: facilities with high quantities of capturable CO2, which drives down the cost per ton captured, and facilities that always have a low cost of capture because of the relative concentration of their CO2 stream. And as we already discussed, those ones are going to be ethanol, oil and gas production, natural gas processing facilities. So now that we've looked at the capturable CO2 that qualifies for the 45Q tax credit, let's look at the supply curve here. So we see that there is a linear relationship when we look at any source that kind of qualifies for this. And generally, the sources cost between $52 to $84 per ton. We're looking at anything below 85. And there's kind of like a $1 per ton increase per 25 million tons of CO2 captured. And indeed, about 850 million tons of CO2 can be captured in the US below the 45Q limit. But it is important to consider that the cost of transport and storage will increase CCS costs. And that's what we have set aside to talk about here. And so thank you. We will now be accepting questions. We have a link to the white paper here, as well as the Concord application and the conference paper that goes more over the literature-based values that Jeff presented at a conference recently. Yeah, and now we will be taking questions. Thank you.
All right. Thanks, Kat and Jeff, for the awesome presentation. A couple questions in the chat right now. First, what do you mean by high purity CO2 sources from oil and gas production?
I could take that one. So from oil and gas production, sometimes you have like acid gas removal streams. And so in that area, you may have like a nearly pure CO2 stream that can be removed at a essentially with only the compression equipment.
Great. Next question is, where does the disadvantaged communities data set come from?
Yeah, great question. So for what's currently in the web application, that comes from the Climate and Economic Justice Screening Tool that's put out by the Council on Environmental Quality from the White House. We've overlaid Concord data against, there's a number of different data sets along those lines that it could also be used with, but that's just what is currently in the application.
Then another question just now came in. Does your cost of capture in dollars per ton estimate reflect the capital cost only, or does that also include the operating cost over some period of time?
It does include the operating cost. And so essentially the cost models estimate the capital cost, and it also includes energy costs based on each state. And it does an estimate on what kind of cooling is needed based on water availability in each state using the US Water Risk Atlas. And then it annualizes each one of those costs using a capital charge factor of 0.096, which maybe that's a little bit too specific, but that uses a financing period of 20 years.
Got more questions coming in. So there's a little bit of a lag in the Q&A on my side. So another question is, are the emissions data gathered into the model only from publicly available sources?
What is currently in Concord is only from publicly available sources. Doesn't mean the workflow couldn't be applied to other things, but yes, currently the original emissions data is from publicly available sources.
And then a follow-up question was, where did the emission volume data come from? For example, ethanol plants do not report their biogenic data to EPA flight. So is this calculated based on plant capacity?
Yeah, great question. It is calculated based on plant capacity. We take plant capacity data both from EIA as well as RFA. They have some plants are in one and not the other, so we combine them together and make sure we're not overlapping with anything else. And then for just the general emissions data, a lot of it comes from the Greenhouse Gas Reporting Program or the flight interface. So we have accessing that data, or EPA's eGrid data for our producing equipment.
Another question is, how often do you update this source data in Concord?
So we update that data whenever there's an update to any of the databases. So RFA and EIA both have so I guess it's the EIA ethanol information comes out yearly. RFA is kind of constantly updating, so we only pull that as frequently as we pull the other databases. But right now we're using 2022 data because that's the most recent data from both eGrid and GHGRP.
Awesome. Next question is, where does the historic data for capture costs, CapEx, OpEx, utility requirements, etc., come from?
So I can speak to that. The cost models are adapted from cost models built by the National Energy and Technology Laboratory, kind of referred to as NETL. And so they built cost models using the help of Shell's Consolve group. And so essentially these cost models were built for like 6 or 7 different industries where they modeled these using Aspen. And then they applied industrial quotes and quotes directly from Shell. And so it's true that we don't have, there's not a whole lot of historical data for a lot of this stuff. It's all very new. But that's also partially why it's important to be able to get some estimates out there.
Yeah, great question. And then also following up on the publicly available data that we take in. So it comes, there's lots of different forms that it comes in. So we need to, we like, for example, the GHGRP, you can access it via flight or via just a summary database. They also have an API where you can get tons and tons of tables of more specific information. So we read in all these tables and process them to get it into a common format. And then once we have it in that format, it goes through the rest of the Concord process to come up with what you saw here today.
Another follow-up question is, can we input any data we have into your models to conduct these estimates ourselves?
Great question. So the current version of the tool, I mean, I guess we would say that the application is like our first prototype of having that. And most of the work that we do, we use it for consulting projects currently, moving in the direction of trying to make it more available. So we have talked with at least one organization about getting some of their own data together to putting it into Concord. That's not something we've done a lot of yet, but I don't see why we couldn't build that into the workflow. We've already thought through about how to do that. But in terms of how the tool is currently set up, if you want to look at it yourselves, it's not quite set up for that yet.
All right. Any other questions? Please put them in the chat. There's past 30 seconds or so, there has not been any new questions. Oh, got one more coming in. How do you manage or go about managing extreme aggregation? I think this question was related to what you just said, Jeff, about all these different data sets coming in together.
Yeah, so we group emissions at each facility based on the type of emission data that it is. And so trying to represent, at least from the screening level, what is closest to what might happen. So if, a facility has a couple of different natural gas turbines they might be close to each other, it might be possible to build a common train to collect that information. So we'd group those emissions together. Perhaps in practice, they are far apart and that's not possible. But for the screen level, we feel that that's an appropriate way to do it. So it's kind of based on the type of equipment, since the similar types of equipment would have a similar type of capture technology and cost for that CO2 capture. I don't know if Kat, you wanted to elaborate on anything there.
I think you captured everything.
All right. Well, I don't see any more questions coming in. So if that's all that we have, I want to thank everybody again for attending. Thank our excellent speakers here, and just remind everybody that the recording of this webinar will be put on our YouTube channel. Oh, one other question just came in. Can we use this model for free?
So the web application has limited functionality. You're welcome to explore that as you will. For most applications or for other uses of Concord, please reach out to us. You can reach out to that Concord email address on the slide right here. Happy to meet with you and talk about how we might be able to use it to meet your needs.
Great. Well, thanks again, everybody. Have an excellent rest of your day, and we'll hopefully see you next month for our webinar in April. Thank you.
Thank you.
Thank you, everyone.